these two masses are moving to the right with speeds v1 equals minus 1 meters to the second to the right, and v2 minus 5 meters per second right. And here there are two masses. And this is after some other forces, other initial conditions, whatever. They're connected by a dashpot with this constant here. And the question is, what is the force on mass 2 here? Which of these things? Okay, and you have 10 seconds to answer the question. Okay, let's seal up the vote. Let's see how you did at it. And let me say how I would deal with this question. So the dashpot itself, if we draw a free body diagram of it, has some tension in it, and we can call this the tension in the dashpot. If we draw a free body diagram of each of the masses, they have the same tension. So this tension here is what I'd call the force in the dashpot. I could have called it the force in the dashpot the whole time, force in the dashpot. Let me just call it that. And that's the same as the force that acts on mass 1. Okay, so here's free body diagrams of the three parts. We could also draw a free body diagram of the whole system, but the free body diagram of the whole system has no forces on it. So there's nothing to say. It doesn't tell us about this internal forces. So here's 4 different free body diagrams we can draw. The key one is actually this one, because the nature of the dashpot is that the force in a dashpot, or the tension in the dashpot, is proportional to the rate at which the dashpot is lengthening, and the proportionality constant is c. So what is the rate at which these things are lengthening? That's the rate of change of the distance between the two things, which is x2 minus 1. That's what L dot is equal to, which is equal to x2 dot minus x1 dot. And we've been given what x2 dot and x1 dot are. x2 dot was minus 5 meters per second. So we have minus 5 meters per second minus this other one is minus 1 meter per second. And minus 5 plus 1 is minus 4 meters per second. So that tells us that this is equal to the 3 newtons per meter per second multiplied by minus 4 meters per second is equal to minus 12 newtons meters per second divided by meters per second gives newtons, because these units cancel. So the force in the dashpot is 12 newtons. That's the same as its force in the dashpot over here. So the right answer is 12 newtons, which is none of the above in the way I calculated there. So that corresponds to A, B, C, D. Okay, any questions about the reasoning or about the answer? Yes?
So the way you have to read it, just not to misunderstand anything, there should be 12 newtons pushing right.
A force of 12 newtons to the left. What did I get here for my answer? Did I do the calculation wrong? Somebody tell what I did wrong? Yes? It should be pushing to the right, but let's just say I did all this calculation right. Here's a force which I've assumed is this one. That matches this one. That matches this one. It should be C times L dot. L dot is the rate of change of separation of these two is x2 dot minus x1 dot. x2 dot is minus 5 meters per second. x1 dot was minus 1. This turns into minus 4 meters per second. So that we have 3 times minus 4 is minus 12. Thank you. Okay. Now, ask your question again. Okay, so by doing the arithmetic correctly, I get the answer that you want to get. The pulling to the left of minus 12 is the same as the pushing to the right of plus 12. If you want to think about it intuitively, this one is going this way slowly, this one is going this way fast. The distance between them is decreasing, therefore the friction between them is resisting that. This is a frictional element, a linear frictional element. It's resisting the relative motion, so it's pushing on that one, so it's a pulling force of a negative magnitude. Okay, any other questions about that? Now I should seal up this vote, and we have a new vote. You can vote about whatever you want. Okay, so now I want to talk about interactions more generally, and then I want to limit myself to a specific kind of interaction, which is a collisional interaction. But we have our basic equation F equals ma, which we can apply for each particle or each mass in a system. And then what we have in a system, if we have many particles, say some kind of machine or masses on an air track or whatever it is, these things interact with each other, and there are forces on each of the masses from the inside and from the outside. And what we're interested now is in the so-called internal forces. And what we mean is forces between masses in the system. And in sort of classical mechanics or in basic engineering practice, we only consider a few kinds of internal interaction forces. So the examples, it's a pretty short list. We have what we call, let's say, springs. So for springs, we have two things. They're connected by a spring. And what we get from that is the free body diagram of the spring. And by action and reaction, we get the masses, the forces on the masses. Now, springs can be of two types. They can be literal springs, or they can be models of elasticity in the system. So when we say a model, we have two things which are somehow interacting. They're connected by something, a piece of rubber, or maybe even they're actually connected to each other. And we say they're connected, but there's not such a tight connection. There's a little elasticity in the connection. And when we go to write equations, we model it as if there's a spring in there. That is, we assume that the force of interaction is proportional to some distance between the objects. Related to that is what I just showed now, is this concept of a dashpot. And the dashpot is drawn like this to represent how it's built if you actually buy it. And the way is, if you buy a product called a dashpot, and it's very much like the same thing that's in a shock absorber in a car or inside a door closer. There's something that keeps this door from slamming. It's some frictional element. And the way they make that friction manageable is they have a long piston. And inside that long piston, they have a plunger. And then they have some kind of fluid in here. That fluid might be air. And then they have a little bit of a leak that comes out like this. And then this is connected over to one object, and this is connected over to the other object. Sorry. This comes out through a hole here like so. And the relative motion is impeded by this fluid flow, and for some reason they call it a dashpot. I don't know what the origin of that. That's some 19th or 18th century word. But these gadgets, anyway, you see them around, like in door closers and in car suspensions or in fancy bike suspensions. But it also has two lives. One is as a literal device, and the other as a model of friction. And usually it's not that great a model of friction, because friction is more complicated. It can be, friction is often like dry friction, which is more or less independent of velocity, or if it's velocity dependent, it often goes as velocity squared. The model here for springs is that this tension follows k times the change in length. The model here for this dashpot is that the tension is equal to c times the rate of change of length, and it doesn't matter how long the thing is. Now, what other kinds of contact, what kinds of interaction forces are there? There's near-Earth gravity, which is an interaction between an object and the Earth. Usually you do not think of that as an internal force. You usually think of that as an external force and don't include the Earth as part of your system. But if you're doing, say, a mechanics of planets and things like that, you have inverse square gravity. Which has this interaction force between two things like this, where this force is proportional to the size of both of the masses. It's inversely proportional to difference squared, and it's proportional to this thing called big G, the universal gravitational constant. There's electrostatic and electrodynamic forces, so all kinds of electromagnetic forces. And for the most part, they don't show up in mechanical engineering practice unless you are actually designing a motor or a generator. But for those people, and I don't think we have any examples in our book where we look at electrostatic or electromagnetic forces. Then the last big class of forces are contact forces. And that's when you have two things touching each other. You have free body diagrams where there's some contact interaction force. And the constitutive laws for the contact forces are variable depending on the situation, and none of them are very accurate. So these contact forces have all kinds of various aspects to them. One is that we can think of them as constraint forces. And what do we mean by constraint forces is you imagine that these things are touching each other, and the nature of the contact is it keeps these two things together. So it's a constraint on the relative motion, and the force finds out whatever it has to be in order to keep the things stuck together. So for example, if you have two parts which are connected at a hinge, if you have, say, for example, in a truss, you can think of the contact between two bars in a truss as a contact force, and the interaction force is whatever it has to be to keep them touching each other. That's in dynamics and statics the same. There's friction forces. So you assume if they're touching each other but sliding, they obey some laws of friction. For example, Coulomb's law of friction with this coefficient of friction mu. And you've done problems like using mu in statics. Or they could be, and this is the last one which we're going to talk about today, there could be collision forces. Okay, so let me just now jump to this last case. Friction forces of this type don't make much sense in one-dimensional mechanics because you have to have things rubbing by each other, stacked up on each other, and we can't really show that too well in one dimension. The springs and dashpots, I did springs in lecture, you do dashpots in homework. Contact forces we're going to save till next section, where we're going to talk about calculating constraint forces. What does it take to keep things moving in a certain way? In other words, you assume some geometric relationship in the motion and find the forces. And then collision forces is what we're going to talk about today. So let's just talk about collision forces. Any questions about the overall logical setup of the course, what the kinds of forces are we're dealing with? All this stuff holds 1, 2, 3 dimensions, but the examples we're doing now are just one-dimensional. Okay. So let's just say we have two objects approaching each other. So let's say one here has this velocity of v1, and this one over here has this velocity v2, and we'll assume that this is v1 is bigger than v2. And now what I'm going to call this situation before the collision, I'm going to use a superscript minus, and this minus means before collision. And if we look at these things, the free body diagram doesn't show very much. Then we have, then they collide. So these things hit each other. When they hit each other, they make some sound. They go bang. They deform a little bit. They maybe break a little bit. Some complicated thing happens in there. And during the collision, we could draw free body diagrams. And the free body diagrams would show an interaction force here, some force here, and some interaction force here. And these forces have to be equal and opposite by the principle of action and reaction, but one does to the other does to the one. We could make a plot of what those forces look like as a function of time. So we're going along here in this minus regime. Then we get to the collision, and this force gets very big and comes down like that. And then we get over to here to this plus regime. And in this plus regime is what we're going to call, this is a before, this is during, and this is after. And the plus regime I'll draw on the next blackboard. So there's some brief period of time when this force is very big. And if these call these masses 1 and 2, 1 and 2, 1 and 2, then we can look at the net effect of that force on the collision. But before I do that, let me just finish the picture and then say after the collision. And after the collision, we have these things moving like so, with a V1 plus and a V2 plus. Plus means after. And usually you assume that V2 plus is greater than or equal to V1 plus. So it doesn't have to be true. You can imagine the possibility of things passing through each other. For example, object 1 could be some cloud of particles in space. Object 2 could be some cloud of particles in space. They could interact with each other. There could be a net interaction between the two clouds of particles, and then they pass through each other. And V1 could still be greater than V2. But mostly you're thinking about solid objects, and you don't allow the possibility of them to pass through each other. So we usually assume no pass through. But as I said, the laws of mechanics don't prevent it, the overall momentum balance laws, and there are physical situations where you might want to think of collisions involving things passing through. Another example would be a bullet passing through an apple. That's a collision, but afterwards the bullet is still moving. So pass-through is still, the calculation works and it does apply. It is relevant sometimes. Okay, so before I go on, let me erase some blackboards. You can look at that. Line up a question while I'm erasing the blackboard. Any questions about this dashpot before it goes away? The homework due tonight? Now, why are you telling us now?
So, problem number 9.3, the notation says make the substitution x equals x minus some constant. So the two x's are different. Each one of those is a different symbol. And then make the substitution based on new variable equals old variable plus some constant.
That's computer speak. X equals x plus 7. Yes? Maybe the hat didn't show in your printing. Maybe the hat didn't show in your printing. Are we using the old book or the new one online?
I was looking at the new book.
Okay. Well, I'll try to post that this afternoon also. You show it to me. Okay. So now, what can we figure out about this collision? What we have to work with is the laws of mechanics. And the laws of mechanics, in this case, are linear momentum balance. And linear momentum balance, we can write three different ways for this problem. We can write for block 1, we can write linear momentum balance, and it says that this interaction force, which is minus F, is equal to M1 x1 double dot. For mass 2, we can write that F is equal to M2 x2 double dot. The same letter F, which is the compressive force between these two things. And in the case of collisions, we violate the general rule that tension is positive, because in collisions you just don't see much or any tension, so it's no point in always having negative numbers. And then we have, for the system as a whole, we can write momentum balance, and it says that 0, the net force in the system, is M1 x1 double dot plus M2 x2 double dot. So any general thing we're going to figure out follows from these equations. It's really all we have in one-dimensional mechanics is linear momentum balance. Where does the system equation come from? You can think of it as coming from a sum of these two equations using action and reaction, or you can think of it as an independent postulate of mechanics that the net change or rate of change of linear momentum for a system is the net external force on the system. This system has no external forces on it, so the rate of change of linear momentum for the overall system is 0. And another way to write this second equation is that the total mass of the system times the acceleration of some point I'm going to call g. And by g, I also mean center of mass. Sometimes I write that symbol like this. The acceleration of the center of mass is 0. So there are two equivalent ways of writing the system linear momentum balance equation. So we still don't know much, and we're not actually going to be able to figure out much until we add more assumptions. But let's just figure out a little bit more. Since we're looking at the situation before and after, it's nice to write the equations and see what we can get about before and after. How can we get before and after from those equations? Is we want to go from before, which was the minus state, going to the after, which is a plus state. And how can we get there? Well, let's just look at mass 1. Let me look at mass 2 to keep the sign convention simpler. For mass 2, we have that F is equal to M2 X2 double dot. We can write that then as the integral of F dt from some time before to some time after. So I'll put this from t minus up to t plus. And I can mark then on this plot a time which I'll call t minus and a time which I'll call t plus. So I can integrate, and then when on the right hand side I can say I have the integral from t minus to t plus of d by dt of v2 dt. The integral of the rate of change of something is just its total change, and so this just turns into m2 times v2 plus minus v2 minus. And the simple language we use for that is that p, and we define this thing to be p, so the impulse, when you use the letter p for it, is equal to the mass times the change in the velocity. And now we can write the same thing for mass 2. And now I have to erase the head of Blackboard. So we can write the same thing for mass 1, which says that P, that same P, is M1. And now I have to put a minus delta. Well, let me just put minus P here, is M times delta V1. And I can write the same thing for the system. And for the system, there's no force. So the integral of 0 dt from t minus to t plus is equal to 0. So I have 0 is equal to m total times delta v of the center of mass. Okay, now ask any questions about the notation or the math or anything else. Yes?
Is P impulse?
Say again?
The P at the bottom of the board right there.
Yeah, so I'm defining impulse. I'm defining to be p, and I'm defining to be the integral over some time interval of interest of the force with respect to time. That's the definition of impulse. And usually you think of impulse as something that happens fast, you bang it, but the word impulse technically in mechanics doesn't have a bang in it. It just means the net integral of force with respect to time. Yes? Come have a long discussion with me. You name a letter, I'll tell you a problem with it. Okay, P also reminds of pressure. P also reminds of tension in Beer and Johnson. J reminds of polar moment of inertia, and the unit vector in the y direction. There's only so many letters in the alphabet, and we're stuck sometimes recycling the letters. So we have to be careful if there are problems for both letters up here.
Sweet Chinese characters.
Yeah. Some of us can, and some of us cannot. Any other questions? Yeah?
What does the ODT stand for?
What is this 0 dt? The 0 stands for the net force on the system is equal to 0. Other questions? Okay, so now we have this thing called impulse, and we have these equations that tell us how things work. So we can summarize what we know about the collision. Is we know that V1, M1 times V1 minus plus M2 times V2 minus is equal to M1 times V1 plus times M2 times V2 plus. Where does that come from? That comes from this equation 3. There's no change in the center of mass velocity. We also know that M1 times V1 plus minus M1 times V1 minus, the difference between these two is minus P. And we also know that M2 times V2 plus minus M2 times V2, plus minus is equal to plus P. And these equations are not independent. We can derive this one from these two by adding them up. So now we have this collision. What is the net change in velocity of the two things? So if you want to think of it in one dimension, these things are flying around along, and they come in and they bang each other, and afterwards, so do it in slow motion. So you run it very slowly, slow motion. They're coming in. They have some interaction. The force builds up. You see some squishing. You model it like you might. You can draw free body diagrams of the object separately. You see that. The forces increase and decreases, and then they end up separating at some speed. What's the speed afterwards? If we know the masses and speeds before, can we find the speeds and masses afterwards from these equations? Yes or no? Well, what do you think of as given? What do you think of as not given? Well, we think of as given you're given the masses, you're given the speeds beforehand, and from that can we figure out what happens afterwards. We want to find V2 plus V1 plus. Let's say we just want to find these two things. Can we find them? Quick poll. All in favor? We can. B, we can't. A, you don't know. C, D, or E? You can. You cannot. For reason 1, you don't know the answer. For reason 2, you don't know the answer. For reason 3, you don't know the answer. Or reasons 1, 2, and 3 are your business. Okay, so those of you who say you can, how could we go about finding these things from these equations? Somebody voted you can? Tell me what to do. Well, usually if you want to solve some equations, you start doing algebra. But a good trick of the trade before you do a bunch of algebra is just count whether the equations and the variables match. Do you have at least as many equations as you have variables? But what do we have as unknown? We have even though we only want to know the velocities afterwards, we have as unknown also this P. So we have 3 unknowns, the 2 velocities afterwards and this impulse. How many equations do we have? This is only 2 equations. Why is it only 2 equations? Because if you add these 2, you get this one. F equals ma for each particle in the system. When you add all the equations, you get the system linear momentum balance, assuming you've used action and reaction correctly in every equation. Just like for statics, if you take all of the joint equations for a truss, add them all up, the net equation is the force balance equation for the whole truss. So we have 2 equations, 3 unknowns. It's not too likely we can do it. Sometimes you can solve two equations for two, not for three unknowns, but you might have three unknowns and you might be able to find one or two of them and not the third. But as a rule of thumb, if you have more unknowns than equations, you're in trouble. Okay, anybody want to change their vote? Can do it, can't do it. You're sticking to this. Tell me how to do it. Yes? So I guess one way of thinking about things is we trust the laws of mechanics. They're incredibly accurate. If you read the first part of the book, I said no one of you in your life are going to find a place where the laws of mechanics are noticeably inaccurate. And we trust that something happens. We throw these together, something happens. So we have the laws of mechanics, which if you believe me and your other teachers are extremely accurate. They're going to work for you your whole life. We have that reality happens, so something must determine it. But there's more to life than the laws of mechanics. There's the constitutive laws, which are the laws of mechanical behavior. So I could have these two same masses, these two same velocities, and a different outcome and still respect the laws of mechanics if, for example, I had not inflated this basketball before class. It'd be the same mass, same velocity, but it wouldn't be as bouncy. And nothing in these equations yet says how bouncy these things are. So in order to solve the equations, I have to add another ingredient, which is a constitutive law. And that is generally the case in mechanics, that you have to work with the laws of mechanics, the constitutive laws, and geometry. So geometry shows up in terms of keeping track of velocities and positions, the laws of mechanics, the momentum balance and force balance, and then usually to solve a mechanics problem, you have to make some assumption about what the relationship is between the force and geometry. In this case, we have to assume something about the material property of the collision. Now we could assume that it's a linear spring between these two things, and then calculate using the spring equations just like last lecture, or we could assume it's a dashpot between these two things and integrate the equations of motion with the dashpot, or we could say something happens quick in between, it's very complicated, and I want to summarize that interaction by something like, how bouncy is this? So the summary, without getting into all the details, is this collisional constitutive law. So the right answer to the question is A, we could not solve this so far. So we need a collisional constitutive law. And Newton realized this. Newton tried to figure out what is the law of interaction of things when they bounce against each other, and he took two pendula and hung things from the pendulum and banged them into each other and looked at how far they bounced up and down. And there's a quote in the book from Newton's Principia about his experiments, swinging balls of yarn together and things like that. And we have what we call Newton's law of collision. And it has this constitutive parameter. And the constitutive parameter is called E, which is called the coefficient of restitution. So we have to put in something about the coefficient of restitution, which I'll do next, but I'm going to erase a board. So the coefficient of restitution works like this. It says that the separation speed is equal to E times the approach speed. And if we're going to calculate that in terms of V2 and V1, if we put V1 on the left and V2 on the right, the approach speed is V1 minus V2 minus. That's how fast they're approaching each other.
Isn't that the separation sign?
Let's be consistent with what I wrote before. The separation speed is how much faster it is going. The second one is going than the first one. Thank you. So if V2 is going faster than V1, then they're separating. And this formula works with negative numbers. How fast are they approaching is how much V1 is bigger than V2 beforehand. And this looks like this. Now I tell you a fact, which in part you're supposed to do, figure out in your homework. The fact is that if E is equal to -1 or E is equal to 1, then kinetic energy is conserved. And your homework problem is to show that if E is equal to 0, it maximizes the loss of kinetic energy. It's one of the few theoretical homework problems that we're going to give you. So when things are very bouncy, the velocities reverse exactly, or they pass. If they're very pass through each other, it's not bouncy, but at least it conserves energy because nothing changes. If things are very dead and dissipative, like there's a piece of chewing gum between these two, energy is lost, and the most energy you can lose is to have the two of them sticking together. So in what we call E equals 1 is called perfectly elastic collision. And sometimes people just call that elastic. And then E equals 0 is called plastic collision, or perfectly plastic. And the word plastic historically means like clay. Clay is, I think the original word plastic applied to clay, not to the things that are made out of, model airplanes are made out of. Is perfectly plastic, or plastic collision is when they just stick together. So imagine a piece of clay between these two things and they just go dud and they stick together. That the elastic case conserves energy is easy to see in the case where one of the masses is much bigger than the other. We have the mass of the Earth and the mass of the basketball. If the basketball bounces up to its original height, that must mean that the velocity it had when it was coming up, just after the collision, is the same as the velocity it had going down. That's a perfectly elastic collision. Is this basketball perfectly elastic? No. Now, how many of you have done the homework problem in calculus where you calculate how many bounces and how long it takes and so on? Who's done that problem in calculus? Who's not? Okay, well, I got a problem for you. How long does it take if this bounces, say, with 0.9 times the velocity each time? How many bounces does it take before it comes to a stop? Quick answer? Infinite numbers. So if we just use the coefficient of restitution model for rigid objects, this would bounce up 0.9 velocity going up to a height. The height isn't 0.9 times the height is square root of that, but then we go 0.9, 0.9, 0.9, 0.9, 0.9, just gets smaller, smaller, smaller forever. And how long does it take? It takes a finite amount of time, which you can calculate from a geometric series. A homework, a little puzzle problem for you is, what if instead of a gravity force, constant force pulling the basketball down, I had hung this basketball from a spring, and the equilibrium position of hanging the basketball was just touching the table. And then I bounced the basketball again and again against the table with a coefficient of restitution of 0.9. How many bounces before it came to a stop? Infinite number again. How long would it take? Puzzle problem, first one to send me an email earns a candy bar. Puzzle problem is basketball hanging from a linear spring. Equilibrium position is just touching the table. Coefficient of restitution is 0.9 or 0.7, whatever you like. How long does it take to come to a stop? Okay, so now given the coefficient of restitution, we have then a third equation. So the collision law gives a third equation. Which means we can then solve for V1 plus v2 plus, and p. And I'm just going to skip the algebra. You can do that yourself. There are various ways of organizing the algebra to make it easier or harder. I'll just let you play around with that. Let me just do a little aside. Any questions about being able to do that algebra? You can calculate the difference between the velocities beforehand. You can use the coefficient of restitution to figure out the differences afterwards, and then work your way back through here. Okay, so let me just make a quick comment about energy. So the system energy, kinetic energy total of the system, is equal to 1/2 mv1 squared plus 1/2 m2 v2 squared. What I'm now going to tell you is a theorem, and it's not a lot of algebra, but I don't want to do that algebra for you because I don't think you enjoy algebra any more than you enjoy MATLAB. So I'll just tell you this theorem. The theorem is that this EK, and this is for the system, EK tot, is equal to 1/2 m tot VG squared. Now, is that right? And the answer is no, that's not right. Plus M2 times V2 minus VG squared divided by 2 plus M1 V1 minus VG squared over 2. Now, how do you figure this out? Is you have to use that VG is equal to M1 V1 plus M2 V2 divided by M tot. Substitute that in there, go through all the algebra. It turns out that's equal to this. A way to interpret this is that the kinetic energy of any system is the kinetic energy associated with the center of mass motion plus the center of mass, kinetic energy associated with motion relative to the center of mass. So the kinetic energy of a whole collection of particles, you can think of it as the net kinetic energy of the particles together. So what's the kinetic energy of these things two moving around? There's some fictitious point somewhere in the middle, which is the center of mass. We look at the kinetic energy of that fictitious point, its velocity times the squared times the mass of the system, and then we look at the motion of the parts relative to that, add that up, it gives us the kinetic energy of all the parts separately. What's your question? It's V1 minus VG in the third one. Any other typographical, chalkographical errors? Okay, now if you understand and believe this, it tells you how to do the homework problem, which is this result over here, that you maximize the loss in the kinetic energy by setting the coefficient of restitution equal to 0. So any quick questions? Okay. See you Thursday.